Hi, everyone. Welcome to our talk. My name is Carrie Edwards, and I'm a senior software engineer at Grafana Labs.
And I'm Fiona. I'm also a senior software engineer at Grafana Labs. And so as a bit of background to this talk, we have both done some small PRs in Prometheus before, but out-of-order native histograms was the first significant contribution we'd made. So we'll be talking about what we did, what we learned, and hopefully encourage you all to contribute to Prometheus. But before we go into all the scary out-of-order details, let's first introduce a few key Prometheus concepts first.
So I know there's already been a lot of really great talks on native histograms, so you've already heard a lot about them, but I'm going to quickly summarize them again. So native histograms are similar to classic histograms. They store a distribution of data points rather than raw data. They're frequently used for quantile estimations. The data is recorded in counts of values that fall into certain ranges, and these are called buckets. So in this example, we have 5 values in the range of 1 to 2, 3 values in the range of 2 to 4, 0 from 4 to 8, and 7 from 8 to 12. The main difference between classic histograms and native histograms is that for classic histograms, you have to define the bucket boundaries yourself ahead of time. This can be difficult to determine what the proper boundary should be, and this might change over time. So native histograms fixes that issue because the buckets are pre-computed and exponentially increasing over time. So I'm not going to get into all of the details of the structure, but some of the properties are important to know for this talk. So the first would be the count, which is the overall count of observations in the native histogram. And then there's also the positive buckets and negative buckets, which store the counts that fall into the buckets. And then there's the zero count, which is the count of values that are 0 or close to 0. And the zero count combined with the positive and negative buckets should sum to the overall count. What is out-of-order ingestion? So originally, Prometheus only accepted in-order samples, which worked well with a pool-based system. But there's situations where you could have samples arrive out of order. This can happen for a variety of reasons, such as network issues, loss of network connection. But another possible reason is push-based metric systems are more likely to send samples out of order. OpenTelemetry is an example of a push-based system, so support of out-of-order ingestion is important for compatibility with OpenTelemetry. So support for out-of-order ingestion was added a couple of years ago, but it only supported ingesting float samples because native histograms were still under development at that time. And another concept we need to go over is chunks. So samples in the TSDB are stored in something called chunks, which are essentially just a set of samples. And there's also what's called the head chunk, which is a chunk that can be written to. Samples contained within immutable chunks need to be sorted for faster querying.
Cool, so how do we get started with the whole project? Luckily, it had already been started for us, so that was quite nice. Thanks to Carrie and Jeanette, thanks to them, there was some initial work for out of order already there, and we also appreciate how helpful they were when we were onboarding into the project too. So the basic implementation was done. However, there needs to be more validation, and we also had to figure out how to deal with some specific native histogram quirks. The first step for us was, well, learning how native histograms and out of order worked. There are some good write-ups and talks on both subjects, but still, they're complex topics, and since we were unfamiliar with these parts of the Prometheus codebase, mapping that understanding to concrete code was tough. What was super useful for us was the test code. So there were a lot of tests for out of order already. Since they only tested for float samples, so we extended them for native histograms as well, so making a map with all the different sample types and modifying each test to run subtests for each type. Just updating the test helped figuring out what was going on when something broke, because we could then jump in with a debugger and explore the code that way. So once we had this understanding, we were able to add additional native histogram-specific tests, and as a bonus, also spotted a few small bugs on main that we fixed.
So here's what we learned throughout this process. One of the first issues we ran into is encoding types. So there's different encoding types for chunks for the different types of samples, and XORs for float samples, and then there's also an encoding type for histograms and float histograms. And because out-of-order ingestion was originally written for float samples, there was a lot of places in the code that assumed the XOR encoding type. So there were a lot of different areas that needed to be changed so that all encoding types could be supported. Another major change that needed to be made involved chunks. So I'm going to walk through how chunks work and then what needed to be changed. So as samples come in, they're initially written to the head chunk. The head chunk has a limit on how many samples can be stored in it. Once the head chunk is full, it's written to the disk as an immutable chunk, which is referred to as memory map chunks or M-mapped chunks. After the chunk is written to the immutable memory, a new head chunk is created, and incoming samples will be appended to this new head chunk. So with chunks, in-order and out-of-order samples need to be handled differently. So there's actually an in-order head chunk and a separate out-of-order head chunk. The reason for this is that when chunks are written to memory, the samples need to be in sorted order. Out-of-order samples can be out of order amongst themselves, and the in-order head chunk is compressed, but the out-of-order head chunk is not, because it would not be very efficient to compress and decompress it when you have to sort the samples. So when a sample comes in, the timestamp of the incoming sample is checked and compared with the timestamp of the most recently added sample in the in-order head chunk. If the incoming sample's timestamp is later than the timestamp of the most recently added sample, then the incoming sample goes into the in-order head chunk. If the incoming sample's timestamp is earlier than the last timestamp added to the in-order head chunk, then the sample goes into the out-of-order head chunk. This process continues as more samples come into the TSDB. But here, we have an example where the incoming sample's timestamp is earlier than both the timestamps of the latest in-order sample and the latest out-of-order sample. So in this case, the incoming sample is still added to the out-of-order chunk, head chunk, but the chunk has to be sorted and stored in the correct order.
Cool. So adding native histograms to out of order wasn't quite as simple as just allowing the histogram types to be inserted into the out of order head chunk. So because these native histogram chunks aren't quite like float chunks, there was a trickier bit of implementation due to something called counter resets. So let's explain how counter resets work for floats first. So Prometheus counters are cumulative and increase over time. The only time the counter value decreases is when, say, a server restarts and the counter resets to 0. So if you query for the raw data for a counter, you'll get something like you see on the screen. The line keeps going up and up over time, and then there's a sudden drop to 0, and then it starts growing again. So the drops are the counter resets. You need to know where they are when you do queries over the counters. For example, let's say we want to find the total count for the time range in the graph. We find the values just before each drop. These are the total for the counter before it's reset, and also the final value in the time range. And then you add them all up, and it gives you the answer. As a couple of additional things, if the value at the start timestamp is greater than 0, then we take the diff between that and the last value before the first counter reset. And also there can be some extrapolation to make sure the time range is covered if the samples don't fully align with the interval.
So how do we detect counter resets? For float samples, it's quite simple. It could be done at query time because it's quite efficient. Since it's just a single sample or a single float value, it just has to be read and compared with the previous sample's value. If there's a decrease in values between consecutive points, then this indicates that there's a counter reset. And when a counter reset is detected, the value is adjusted by adding the count with the previous sample's count, as Fiona just described. So with native histograms, it's a lot more complicated. We're still looking for a drop in value to detect the counter resets. However, there's 3 separate properties that need to be monitored for the drop in value. The first is the overall count of observations in the native histogram. So if that value decreases, then that indicates a counter reset. The second property that needs to be considered is the count in the individual buckets. So if the value in a single bucket decreases, then this is also a counter reset. So to check this, you have to loop through every bucket and compare with the previous values in that bucket. And the third property is the 0 count. So you can see here that the counts go up, the overall count goes up, and the bucket counts either stay the same or increase, but the 0 count decreased, so that is also a counter reset.
So because it's more complicated, it's slower to detect counter resets for native histograms compared to float counters. So therefore, instead of doing it all at query time, Prometheus will attempt to detect counter resets for histograms at ingest time too. So if a counter reset is detected, a new chunk is created, and histogram chunks have a counter reset header denoting whether the chunk was created because of a counter reset or not. This way, you know it's only possible for the first sample in a chunk to be a counter reset, or another way to put this is a counter reset can't happen in the middle of a histogram chunk. So the benefit of ingest time detection is that you don't need to always go through the internals of each histogram sample at query time to find the counter resets. Though this isn't all completely foolproof, because say you have overlapping chunks that you're reading, then you might have to re-figure out some counter resets there. So this change in the way that chunks work for histograms meant that some changes had to be made for both in-order and out-of-order ingesting for histograms, but just for the sake of this presentation, we'll just go through a couple of changes that had to be made for out-of-order.
So a new chunk has to be created for each counter reset, and this required a change in how chunks are handled in other parts of the code. So originally, the code expected there to be a single chunk. Now, when the head chunk gets full or reaches its max capacity, and it's being written out to memory as an immutable chunk, it can be split up into multiple chunks if there's a counter reset. So in this case, there's actually 2, and so this will be split into 3 different chunks. And when there's a new chunk from the counter reset, samples will continue to be appended to that chunk until there's another, if there's another counter reset. This was a major refactor in the code because we had to update everywhere that assumed there was a single chunk to handle multiple chunks.
Cool. So another area which was affected by counter resets was when reading from the out-of-order head. So that includes the out-of-order head chunk and also out-of-order in-map chunks. With out-of-order, you can get chunks that overlap in time since samples just can be out of order with each other. So with the original float implementation, to read from the out-of-order head and in-map chunks, all chunks that overlap the requested time range were collected together, and we pretended that they were a single chunk. This was fine to do so. It satisfied all the expectations of a single chunk when being read. One note here is also that chunks aren't rewritten into a single chunk when we gather them, they're just merged when the samples are read. So one requirement of a chunk that we've been through before is that samples should be ordered, and so the out-of-order merged chunk iterated through the internal chunks to always return samples ordered by timestamp. In this example, for example, we get T0 from chunk 1, then T1, but then we switch to chunk 2 because the next sample is T2 from there, and then back to chunk 1, and so on. Also, as mentioned before, a chunk requires there to be no histogram counter resets in the middle of the samples in the chunk. In this case, well, all the samples are floats, so you can't get a histogram counter reset, which is quite nice. So there are parts of the code that depended on this merged chunk basically behaving like a proper chunk and could error if it didn't. Of course, once we added native histogram support to out-of-order, suddenly this out-of-order merged chunk didn't behave like a proper chunk. So samples still get returned in order, but there could be a histogram counter reset in the middle of the sorted samples, while each of the individual chunks are guaranteed to be sorted within them and not have a counter reset. If you combine them together, this might cause a counter reset. For example, say you start reading from chunk 1 in this example, and then the next sample comes from chunk 2. The first sample from chunk 2 can be a counter reset compared to what's in chunk 1. So to adapt for this, we had to extend some methods that read chunks. So originally, the chunk reader would always return a single from a chunk for a given reference. Now it can still return that, for example, for in-order stuff, but it can also now return an iterable over samples, and that can form multiple chunks, and it's up to whatever function's calling that to form the proper chunks, and that's what we use for out of order. So I assume you're very curious. What's up with the PR now? We've covered a few of the challenges with the implementation, and about the current state of the PR. It's currently in review and hopefully will be merged soon. Since it's experimental, it's going to be off by default, and there'll be a feature flag to turn on. If you've not contributed to Prometheus before, I'm sure this presentation has made you really enthusiastic to do so. There are always plenty of issues to take on. One thing for us about the experience was it was intimidating to actually start work on like an open source project that's so visible and used widely. Prometheus is a complex project and it takes time to get comfortable and figure stuff out. But we did it, or are doing it, because still need that last PR merged in. But yeah, it was good, learned a lot, and obviously got helped out a lot too. We do want to share a few tips from our experience of contributing. So one of the main ways we got more comfortable with Prometheus was with testing, as we've mentioned before. It was a big part of helping us understand how out-of-order native histogram works, and debuggers are always useful. It's also helpful in retrospect because there were a bunch of tests already, we were fairly comfortable with making changes, knowing that a previously written test will probably catch any issues as we started with the code. The next thing is also incremental PRs are always nice to reviewers because they're smaller and they're easier to roll back if there's something going wrong. But in our case, it was actually a bit hard to make incremental PRs because we are unfamiliar with the code. So what we actually did was we first made like a big draft PR and made all the tests and changes there, and once we had that, we had a better understanding, at which point we can extract them into smaller PRs and be more polite about what we were asking reviewers to read. Next thing here is documentation. Documentation is also always good for people who come afterwards, like whether that's adding stuff in code or just rough notes in the doc to be shared later. So in terms of how to get help, how to contribute, well, there's probably people here you can talk to ask on how to on specific things you want to do. But also the CNOCS Slack, there's a bunch of Prometheus channels there if you have any questions. And there are also Prometheus office hours, which are linked here. I'm sure we'll share the slides in some way, I hope.
So even if you have contributed to Prometheus, native histograms is another great area to contribute to if you're interested in it. It can be a bit tricky compared to float samples, but while I was learning about native histograms, I wrote a doc to be sort of a developer guide that's linked here. This tries to explain some of the trickier concepts as well as the data structure. It's still a work in progress. I'm working on it and updating it as I have time, but feedback or questions on that would be welcome and encouraged. I also added a link for the open issues currently in native histogram, on native histograms in Prometheus. And you could also contribute to this project. There's still plenty of opportunities to improve the code through deduplication, refactoring, and optimization. So if you're interested in that, we would love to have more contributions there. I added a couple more resources here. The first is just generally a resource on Prometheus that actually lists a bunch of different resources. So you can get started on that. And then the second link is to our colleague Ganesh. He has very good blog posts on the TSDB. And more of our colleagues also did out-of-order support in Prometheus and PromCon 2022. So there's a link to that. Thank you so much for listening.
Amazing. Questions? Any questions that you might have?
I have one.
Yes. Oh. Yeah, go ahead while I walk slowly.
I noticed that there are two feature flags, one for native histograms and one for out-of-order native histograms. Why two?
So we wanted to make sure that we didn't break out-of-order ingestion for float samples. So while we did a lot of testing, we just want to be careful. And so we have the feature flag for out-of-order ingestion of native histograms enabled until it's been more thoroughly tested. So yeah, that's why.
Okay, thanks. I have a question regarding chunks and the fact that when they are persisted to disk, that they are immutable. Like if you have out-of-order ingestion, like, how far in the past can you accept new samples? Because like, if there is no limit, then if I understand correctly, you have to look forward a lot into chunks to get the data, right? Or maybe I'm just like lost.
For querying?
Yeah, for querying, yeah.
I think there is you can configure a limit, I believe, on how far back to accept out-of-order samples. But for querying, you just can add in here, but it will pull up it'll look through all of the chunks in that time range that you're querying, and then sort the samples based on that, because you can have chunks with that are missing some, and then have a different chunk with out-of-order samples. If that helps, is there anything else you want to add?
I think that's fine, unless you have follow-up.
Does that make sense?
Yeah, kind of. Like, okay, yeah. Thank you.
I have another if nobody has. Here.
Yep.
I noticed how counter-reset hints are the trickiest part for out-of-order ingestion. There are a few formats that has some kind of hint. It's not the same. But for example, TLP provides start time Unix nano. Mm-hmm. It's not the same, but it could be used as a hint. Open metrics, we are also working on simplifying the created timestamp. Would that help somehow if you have this information on before ingesting?
The start time?
Yeah.
I believe that is more that's for delta temporality. Oh, that's the way that it's tracked with delta temporality. So, yeah, I don't remember the exact details of how that works for detecting out of order for OTEL, but anything?
Yeah, I'm trying to think through it. I guess it might help with the first bit of like detecting out of order, but yeah, I guess I don't know whether when you start merging chunks and there being multiple chunks, you might still have the same issue of like, oh, there's different chunks that somehow have the counter reset in them, but yeah.
Okay, great. Thank you again for your talk.